Let's look at the features of TCP. First feature is byte streaming. Whatever bytes are obtained from the application layer, TCP converts them into segments and sends it to the receiver as shown in this animation. Next, connection-oriented protocol. That is, in TCP, we have three-way handshaking before any data exchange. Next feature is full duplex. As shown, both sender and receiver can simultaneously send data to each other. Next feature is flow control. In this, according to the capacity of receiver, the sender synchronizes the rate at which data is sent. Here, as the capacity of receiver is overwhelmed, so the sender realizes and then synchronizes the data. One of the most important features of TCP is congestion control. Now suppose the data is being sent like this. Suddenly, this is the state of congestion. That is, the network capacity is being exceeded. TCP controls congestion by synchronizing according to the capacity of network. Here is a graph demonstrating how the congestion control takes place. First, we have this exponential increase, which is called slow start phase. As soon as the threshold is reached, the linear increase starts, which is called congestion avoidance phase. At last, when maximum receiver capacity is reached, it becomes constant.
Next, we analyze how RDT 2.1, that is Reliable Data Transfer 2.1 protocol, handles acknowledgements and negative acknowledgements. This protocol has error detection for packets as well as for ACKs and NACKs. In case ACK or NACK are corrupted, this protocol also takes care of it by handling the duplicate packets, and for that it uses a sequence number that is either 0 or 1. This is suffixed, and using this sequence number, it tries to detect the duplicates. On the center side, we see we have 4 states. That is, first it waits for the call 0 from above, second it waits for ACK or NACK for call 0, third it waits for call 1, fourth it waits for ACK or NACK 1. Whenever a data has to be sent, a packet is created just like in RDT 2.0, and here an additional sequence number 0 is added along with data and checksum, and the packet is sent to the underlying layer. This, after sending, in case a positive acknowledgement 0 or NACK 0 is received, there are 2 possible cases. In case the packet is corrupt and NACK is received, then the packet is resent to the underlying layer. And if a positive acknowledgement is received, then nothing is done. It waits for call 1 from above. Again, the similar process is repeated. It sends the data by creating a packet now with sequence number 1, because last time it was 0. On creating the packet, it sends to the underlying layer using the same function. Again, it waits for ACK 1 or NACK 1, and accordingly, if it is NACK 1, it resends the packet, and if it is ACK 1, it does nothing and waits for call 0 from above. Now let's see how the duplicates are eliminated. Here, if ACK 0 is corrupted, that is, instead of ACK 0, NACK 0 is sent, then the packet sent would be with sequence number 0. But last time also the packet sent was with sequence number 0. So we have 2 consecutive packets with sequence number 0. In that case, one of the packets would be discarded and the other packet would be used to deliver the data. Now we will have a look at the receiver side of RDT 2.1. Whenever a packet is received with sequence 0 from the underlying layer, and the second state whenever a packet is received with sequence number 1 from the underlying layer. Now, if the received packet is not corrupt and has sequence 0, then obviously it will extract the data from it, deliver it, and send a positive acknowledgement along with the checksum. Now, this checksum is sent with the acknowledgement to detect in the corruption. After this, it waits for the packet with sequence 1. If a packet is received and it is corrupt, then it sends a negative acknowledgement along with the checksum, and this packet is again sent to the underlying layer. Further, if the received packet is not corrupt, but it has sequence 0. Now, in this case, we have it was waiting for call 1, that is packet with sequence number 1, but it got a packet with sequence number 0. So it will resend the positive acknowledgement which was corrupted earlier along with the checksum, and it will send it to the underlying layer. But if the received packet is not corrupt and has a sequence number 1, so that is what was expected in this case, packet with sequence number 1 and it was not corrupt. So it will extract the data, deliver it, and send a positive acknowledgement to the underlying layer. At this state, if it receives a non-corrupt packet, that packet is errorless, but the sequence number is not what is expected, that is 1 in this case. So here again it will resend a positive acknowledgement to the underlying layer, and if the packet is corrupt, in that case it will send a negative acknowledgement to the underlying layer.
So we have often heard that TCP is a reliable data transfer protocol that is built over an unreliable network. In that context, we should always know what are reliable data transfer protocols. In the previous section, Satoshi must have explained how reliable data transfer protocol 2.1 works. Here I'll be explaining how RDT 2.2 works. Let's take a scenario where we have a sender and a receiver. The sender sends the packet 0, the receiver gets the packet. The sender is now thinking, is my packet acknowledged? And then the receiver sends the acknowledgement of packet 0, and now the sender knows that the packet is acknowledged, so it's good to go. It will now send the next packet. Let's say due to the unreliability of the medium, when the sender sends the next packet, it got corrupted in between. The receiver will see that the packet is corrupted. In that situation, what the receiver will do is that it will send the acknowledgement of previous packet. The sender, upon hearing this, it will see that it was waiting for acknowledgement of packet 1, but it received acknowledgement of packet 0. That would mean that something must have got wrong in between. Therefore, it will resend. It will resend the packet 1, and now acknowledgement of packet 1 is exchanged, and now the transfer of packet 1 is complete. Let's see if some other kind of unreliability is introduced in the medium. What happens? The exchange of packet 0 happens. Now the sender sends packet 1. The receiver sends the message that packet 1 is acknowledged, but due to unreliability, the sender heard that packet 0 is acknowledged. But the sender would think, I was waiting for acknowledgement of packet 1. I received acknowledgement of packet 0. That would mean that due to unreliability of the medium, something must have gone wrong in between. Therefore, it will resend the packet 1, and thus the transfer of packet 1 will get complete. So this is how RDT 2.2 works. For RDT 3.0, there is a clock introduced in between so that the sender can know if the packet is lost or there is a delay in receiving the packet. But that is for some other time. Thanks.
First, we will look at pipelining. So this is a non-pipeline case in which we send a packet and then wait for acknowledgement, then send another packet. If we do this, then the utilization of the link is very less. This is why we use pipelining, where we send one packet after another packet and then wait for cumulative acknowledgement. There are two protocols to do this: go back and selective repeat. So in go back and, we can see that these light blue colored packets are all the ones that the sender has sent and are yet to be acked. We can see that the 12th act has been received, so the window will move forward by 2 places. Now we can see that the sender will send 3 more packets, 18, 19 and 20, and then wait for their acknowledgement. After that, we can see that the acknowledgement has not arrived and a timeout event has occurred. So what happens in this case is the sender transmits all of the messages that are in the pipeline that have been unacked. So the retransmission happens. This is selective repeat. In this case, only retransmission of selective packets for whom timeout has happened will occur. So we can see here even out of order packets can be received by the receiver. So 12th packet has been acknowledged. So we can see the window is not moved by 2 places. It means that only the 12th packet has been acknowledged. We can see that 11th packet has been acknowledged and now the window will move forward. We can see that the 13th packet, its acknowledgement cannot be received. So there happens a timeout event at the sequence number 13 and a retransmission for only that packet happens.